Okay, well, welcome once again. We're getting to the end of the year, and we're running out of tests to review for. So this will be one of the last ones. We'll do this performance review and gas law, and then we will push on to the final exam. All right, so let's get started. First, I guess this is going to be my key, and we got to know which way equilibrium is shifting. So all I know about equilibrium is that I can change three things. I can change concentration, I can change temp, and I can change pressure. And I also know that pressure changes only affect everything when everything is in the equation is in gaseous form. So I have gas, 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 gas. So pressure is in play. So we have concentration changes, temperature changes, pressure changes. Now, anytime I increase, it's going to move to the other side. Anytime I decrease, it's going to move towards that decrease. And any increase in pressure is going to move to the lowest mole total. So my decision tree is pretty easy. Am I adding something? Am I removing something? Or am I increasing or decreasing pressure? Pressure, it's not a side that you're doing it to. Pressure is on the whole system. So let's see how this works. I am adding NO. NO is a reactant. Man, that's kind of lighted out. Let's see. There we go. NO is a reactant. So if I'm adding NO, equilibrium is moving to the other side, so equilibrium is moving right. Pressure is increased. Well, we're already going to pressure, so pressure, you have to look at coefficients. The coefficients tell me how many moles. So I have 2 moles of NO and 1 mole of H2. So on this side, I have 3 moles. On the other side of this arrow, remember everything for equilibrium is in relation to that center arrows. So on the other side, I have 1 mole of N2O and 1 mole of H2O, so I have a total of 2 moles. Pressure is increased. It's going to run to the side with the lowest mole total. Since the right side has 2 moles, I am running to the right side. The system is cooled. Now again, heat we think of as just another reactant or another product, so I'm either adding it or removing it. If I'm cooling the system, then I'm removing heat, therefore equilibrium is moving towards that thing that I'm removing. So that is to the right. N2O is added. N2O is a product. If I increase the products, then equilibrium is going to move to the reactant side. H2 is removed. Remember, anything that I removed, it's moving towards. So H2 is on my reactant side, so I'm moving towards it. H2O is removed. H2O is a product. Again, if I remove something, it's moving towards that. So if I remove water, equilibrium is moving to the right. It doesn't matter what it is or where it is. All you need to know is if I increase the concentration of it, then I'm moving away from that increase. I'm trying to rebalance my level. So if I increase NO, I'm moving to the right. If I increase H2, I'm moving to the right. If I increase N2O, I'm moving to the left. If I increase H2O, I'm moving to the left. If I increase heat, I'm moving to the left. Okay. Now then, a energy reaction diagram here. Reaction coordinate. Okay, so in this diagram, they're asking me what a few things are. Well, A, and this line should go all the way to here, is reactants. Reactants. The reaction hasn't started, so it's reactants. B, well, if this goes all the way down to where the reactant line is, which we're going to make believe it does, then that is activation energy. And if you want some practice, if you're having a hard time remembering that activation energy it's from reactants to the top of the hill. It's like, how far up the hill do I have to go to get this reaction started? You can do it on the 2 diagrams below. You can actually show me what is the activation energy. And here, remember, it's from the reactant line to the top of that hill. The reactant line to the top of that hill. And I could have put it outside the line too. I could have just said, okay, these 2 lines I'm measuring from here to here, and that is activation energy, or E sub A. So in this case, B is activation energy. C is the activated complex, right? Activated complex. And I could get long and windy about what an activated complex is. It's neither reactant nor product. Like some bonds have been broken, some have been reestablished, some have more bonds than they normally have. But what you have is you have this big jumble of molecules that are not reactants and not products yet. They are an activated complex. I don't know how else to say it other than activated complex. It's also called a transition state, but nobody likes to use that term anymore, so let's just go with activated complex. D. Well, if A is reactants, then what is D? Products, quite obviously. Products. Which letters will change with the addition of a catalyst? Well, this assumes that you know what happens to this diagram, this reaction coordinate diagram, if I add a catalyst or an enzyme. They're the same thing. In biology, it was called an enzyme. In chemistry, it's called a catalyst. But what it does is it lowers activation energy to speed up reaction rate. Now, it does nothing to equilibrium. Nothing. A catalyst does nothing to equilibrium. The concentrations after this reaction happens are still the same. The concentrations are still the same. But it lowers activation energy. So they're asking me which letters will change. Well, B will change because that arrow will drop down to here. And C will change because the activated complex will drop down to here. So I'm going to go with B, and C will change. Anything measured from the top of the hump basically will change. Anything not measured from the top of the hump will not change. Okay, this energy diagram has high-low activation energy. I don't like that because you're using a subjective word, high or low. Well, how much energy? Is this 5,000 joules or 5 joules? But what they're getting to, what they're trying to get at is endothermic reactions, and this is an endothermic reaction. The products end higher than the reactants. Where did they get that energy from? I had to add it in, into. So endothermic have a bigger, larger activation energy than exothermic. And it's visible down here below. So this is exothermic. The products are lower than the reactants, and it has a relatively small activation energy. And this is endothermic. And if we look at that same line, it's much bigger than this one, right? So endothermic have a larger energy. So what they're looking for is, since this is endothermic, it has a high activation energy, which is most closely associated with endothermic reactions. I don't like the use of the term high and low with chemistry because that's a subjective term. High could be 5,000 or 10,000 or a bajillion. So anyway, but what you need to know is that activation energy is higher in endothermic and lower in exothermic. And I think that's the point they're trying to make. All right, now, number 5, an unstable arrangement of colliding particles that arranges to form products is called the activated complex, right? Activated complex. Activated complex. So if I had NaOH plus H2O goes to, no, let's use something else. Let's use MgCl. We'll do this. MgCl, then it goes to MgOH plus NaCl. In between, at the top of this, you're going to get what's called an activated complex. So you're going to get some of these bonds breaking and some of these things reconnecting. So you're going to have an Na, and it's going to be partially connected to an OH, and that OH is going to be partially connected to a magnesium. And it's going to look like that, right? And you're going to have a Cl, which is also going to be connected to each loosely through these electrostatic things. It's called an activated complex. It's neither reactants nor products. It doesn't look like an NaOH. It looks like an NaOH MgCl all at once. And it doesn't look like any of the products. It doesn't look like MgOH. It looks like an NaOH MgCl. It looks like a big mess, right? That's what an activated complex is. It's not quite reactants, not quite products. The colliding particles are rearranging and they're forming this activated complex. The energy to start a chemical reaction, we know this is activation energy. If I strike a match, I'm adding activation energy through the friction on the side of the box, and I'm adding that heat. Activation energy. And then once it starts, then the match is burning. That's called combustion. A compound that speeds up chemical reaction without being consumed in the reaction. That is a catalyst. All a catalyst does is speed up the reaction by aligning or orienting the two particles to where they can collide more effectively. So it's basically helping the orientation. You got to have correct orientation and correct energy. Collision theory says that I have to have those two things. A catalyst is just making sure the orientation is correct. And because of that, it reduces the amount of energy required. The average kinetic energy of particles increases, decreases as temperature increases. Everybody should get this, increases. You know that as I heat things up, particles start to bounce around faster and faster. That's really what a measure of temperature is how much kinetic energy this piece of wood has, or how much energy this pencil has. All those particles inside that pencil are moving. All those particles inside this piece of paper are moving. Depending on how much energy they have, the temperature is either high or low, right? So the average kinetic energy of particles increases as the temperature increases. All right. Most of this is just theory. It's really quick, but you have to memorize it. Like you have to know. All right, now we got the 5 things that affect reaction rate. It is not the 3 things that affect equilibrium, although a couple of them are the same. So the 5 things that I can do, I can increase concentration. And all of these are directly proportional, which means if I increase concentration, that seems like wow, am I really spelling things that wrong? No, looks like I'm spelling it right. So concentration, I can temperature. I can increase temperature. That increases the rate of reaction. I can increase concentration. That increases rate of reaction. I can add a catalyst. That increases rate of reaction. I can increase surface area. That increases the rate of reaction. And last, I can use the reactivity of elements. And what I mean by reactivity of elements, I'm not going to let the light go down on me this time. The light will not turn off. What I mean by reactivity is I can run the same reaction using either sodium or potassium. Potassium is more reactive than sodium. If I run this reaction and I want to run faster, I should use a more reactive. Remember, reactivity goes down into that corner and up into that corner. If I really wanted to increase the speed of this reaction, I would throw in cesium instead of either of these, or maybe francium. So that's what I mean by increasing reactivity of the element. If I want to run the same reaction with a different element, I can run the same reaction with a different element, and it might go faster. And then they're asking me which one of these I'm affecting by doing these things. So firewood is chopped into small pieces. Well, what you're doing is you're increasing surface area. Like when you make kindling, when you start a fire and you use kindling, you're increasing surface area. And a black powder called manganese dioxide causes hydrogen peroxide to decompose faster than normal. The powder is not used up. Oh man, I thought I'd beat the... Hey, come on. Are you kidding? Oh, I thought I... What the heck? Come on. Stupid light. Oh, okay. We got 10 minutes. The powder is not used up during the reaction. This is the key here. If it's not used up, then it's a catalyst. So they're trying to let you know that it's helping the reaction but not being used up. Food left in a refrigerator lasts longer than food left out at room temperature. That's because there are two reactions. You're creating all these things when food goes bad. You're creating all these things that happen. You can delay that by lowering the temperature. So this is a temp change. Okay, now this last one, they say it in a confusing way. Both of them use a 1 centimeter piece of magnesium. Here they're using 2 molar HCl, 20 milliliters of 2 molar HCl mixed with 20 milliliters of water. So they're diluting it. Here they're just using 40 milliliters of 2 molar HCl. So effectively what they've done is they've made this 1 molar HCl, and this is still 2 molars HCl. So basically it is a concentration change. Concentration change. Okay. Okay. What would happen to the reaction rate if temperature was decreased? Well, remember, they're directly proportional. Concentration and temperature are directly proportional. If I increase concentration, I increase rate of reaction. So if I decrease temperature, I decrease rate of reaction. So that's a 1. Concentration was increased. Well, we know what we said about that, directly proportional. If I increase concentration, I increase reaction rate. Surface area was increased. Again, it is directly proportional. Increase in surface area, increase in reaction rate. Color of the reactants was changed. No change. Color has no effect on anything. An inhibitor was present. An inhibitor is the opposite of a catalyst. So if a catalyst speeds a reaction up, what does an inhibitor do? It decreases the rate of reaction. And last, if concentration is blank, the faster the reaction rate. Well, if I want to increase the reaction rate, I increase the concentration. So that's 2. Increase the concentration. All right, determine the rate of reaction. Oh my gosh, am I going to need a calculator? Okay, determine the rate of reaction. Okay, so this is a rate of reaction problem. So I know that it is concentration final minus concentration initial over time final minus time initial. So what am I putting up top? My initial concentration is 5. My final concentration is 1.5. 1.5 minus 5. So that's going to be a negative 3.5 over. And my time final is 1 minute 16 seconds. And all reactions start at 0. Unless they tell you it starts at some other time, it starts at 0. So instead of subtracting, I'm just going to go with my final time and go 60 seconds plus 16 seconds is 76 seconds. And so negative 3.5 divided by 7.6 equals negative 0.460 molarity change per second. Negative 4.60 per second. That's the molarity change that's occurring in this solution. And it's negative because it's disappearing. I started at 5 molar, I ended at 1.5 molar. That means it's disappearing. That means it's a reactant. Okay, next. All right, concentration final minus concentration initial. Concentration final is 0. It says when it changes during a reaction to 0. That means after the reaction is over, it is 0. So 0 minus 7 equals negative 7 over 3 minutes and 13 seconds. So 180, 193, 193 seconds. This is equals negative 7 divided by 193 equals negative 0.036 molarity change per second. Also a reactant. It was disappearing. It started at 7 molar, disappeared to 0 molar in 193 seconds. So it is negative 0.036. Let's see if I can keep this thing from going off on me by occasionally waving at it. All right. That's straight up plug and chug. You've got a formula, and this is the formula for average rate of reaction or reaction rate. I don't know how you want to. So whenever you see rate of reaction, you should be thinking of this formula. And just remember, chemistry loves final minus initial, final minus initial, final minus initial. Okay. Then they give you the thermochemistry equation of Q equals mc delta T, and they're asking you what these things are. Q is heat added in joules. C is specific heat in joules per gram degree centigrade. M is mass in grams. And delta T is change in temp. Don't tell me temp. It's not a temp. It is a change in temp in degrees centigrade. That is it. And then below that, they give me a question that they want me to use that lovely thing on. So I just have to decide where it fits into that formula. 435 joules. Well, that's Q. And then they're giving me a mass, so I have the M, 3.4 grams. They're trying to determine the specific heat, so I know I'm going to calculate for C. And then they've given me a temp change from 85 to 21 is 64 degrees. All right, now we just got to calculate this. So I'm just going to do 435 divided by, I'm going to do parentheses and do 3.4 times 64, close parentheses, and that gives me 1.9999. So C equals 1.99 joules per gram degree centigrade. And that's it. That is plug and chug. All right, how many joules are contained in 250 calories? 1 calorie equals 4.184. Now, the trick here is that they're tricking you. This is small c. And in every small c, there are 1,000 big C's, or there are 1,000 small c's in every big C. So this is really 250,000 small calories, little c. And if each one of those is 4.104, it's 4.184 times that, which is a million and some change, right? I don't care about that. That's not important to me. I'm going to move on past that because I just don't care about changing joules to calories. Okay, Hess's law. Hess's law. Now, one day you may have to do something with this, but basically what Hess's law says is that I can take the reverse reaction and the reaction forward, and if I find out the energy of those two and it's just the things here, then I can add those things up and get a delta H. Well, here they've figured out the equations of the reactions for you. Usually you'll have a series of reactions and you'll have to pick out the ones that eliminate, because there's no O2 in this reaction, right? So it has to be O2 on both sides to eliminate. There's CO, there's CO2, so I got CO and CO2. I got NO on this side, so it looks like if I eliminate those O2, are perfect. The main thrust of this, and you won't have to calculate that until you get to a higher level chemistry than high school chemistry, but you add these numbers up. So if I add negative 566 plus negative 180.6, I get negative 746.6. And yeah, that's in kilojoules, and that is how much energy it takes to run this reaction. And it is a negative number, so it is exothermic. All right. Now, we got to think about phase changes. When I go from a solid water, ice, to a liquid water, water, Am I adding energy or taking energy out? Well, if you want to melt an ice cube, you better be adding energy in. Endothermic. And so that means that everything moving up a heating curve is endothermic, and everything moving down is exo. We could just think of it that way. Or if we want to go from a gas to a liquid, it has to hit the side of your cup and it has to cool down. So I have to take energy out of the system, exothermic. It's not just things that give off energy. It's also things that I can pull energy out of the system, right? Negative delta H. We already talked about this one, but I'm going to draw a diagram just to show you. All right, so we have this reaction coordinate diagram, and we have this reaction right here. And this is energy. It's actually called Gibbs free energy. We're going to call it energy. We're going to call this time. So moving forward, and we're going to say that this is 20 kilojoules and that this is, the products are at 5 kilojoules. Now, we have to determine delta H. And remember, delta H is in between these two. This is delta H. And we don't know if it's positive or negative yet, but what we do know is that H final minus H initial equals delta H. All right, H final, 5 kilojoules, minus H initial, 20 kilojoules. Means that delta H is equal to negative 15 kilojoules. If delta H is negative, it is therefore exothermic. Exothermic. That means that 15 kilojoules was leaving the reaction, that's what the negative means, as heat. So what do endothermic look like? Endothermic will have a positive delta H. Your products will be higher than your reactants. The numbers will be reversed. 20 minus 5 would be 15. So we can do that. We can show what that looks like, right? We start low, we end high. So we're 5 kilojoules and we're at 20 kilojoules right here. Final minus initial, 20 minus 5 is 15. This is a positive delta H equals 15 kilojoules. That means that I had to add 15 kilojoules into this reaction. That means that it is endothermic. You should know just by looking. Products lower than reactants, exo. Products higher than reactants, endo. Okay, so back to work. Negative delta H, exothermic. You should memorize that one, especially if you're going to use chemistry ever after high school, because negative delta H's, you're going to deal with that a lot. Energy is a reactant. Okay, so let's do a reaction. It's a reactant. We're going to add 416 joules into this reaction, into, endo. Okay, endo. Energy is released. So if it's at the back part, if it's released as a product, then it is exothermic. I'm running out of ways to make my point, but hopefully you will just memorize these things. Phase changes, you got to know. Got to know whether they're endo or exo. Negative delta H, you got to know. And these two should be self-evident. If I'm giving heat off as, if I'm taking heat in as a reactant, it's endothermic. I'm adding energy in. If I'm giving it off, it's released, it's exothermic. All right, this is a throwback to solubility here. To get more gas into the solution, you must decrease temperature. Remember that solution and gases were what? As temp increased, solubility decreased. So we wanted it cold and at high pressure. So we want to decrease the temperature, increase the pressure. That's a solubility question. I'm not sure why it's in here, but whatever. In endothermic reactions, energy is absorbed as bonds are broken. This makes the delta H positive. Endothermic are positive. I know it's a short review. It's 30 minutes, but I hope it helps you out. If you have any questions, you know I'm going to be here at 6 a.m. tomorrow. So come one, come all. Ask your questions, and good luck on the test tomorrow, guys.